All right, now onto the meat of the unit, and that's the voltaic cell. So the backbone of a voltaic cell, or this unit, is the spontaneous redox reaction. So a redox reaction, remember, is a reaction where we have something that is accepting electrons from something else in order to be oxidized and reduced. So in this case, if we take a strip of zinc metal and put it in a copper, in this case it looks like a copper sulfate solution, so that means it would have copper 2+ ions in it. So what's going to happen is the copper 2+ ions are going to accept 2 electrons from the zinc to form zinc ions and then copper solid. So as this is happening, the zinc ions are giving 2 of their electrons to the copper ions, which means that zinc is being oxidized and copper is being reduced. And as this is happening then, the copper is turning into a solid, and so it's going to start getting deposited on this zinc bar or strip that's in there, and the zinc itself is going to dissolve into the solution. So we're forming copper metal and then zinc ions. So when this happens, the zinc goes aqueous and dissolves into the solution. So over time, what we'll see is copper, which has that kind of that golden color, is going to start forming on this bar. And then this solution right here, as the blue copper ions are disappearing, is going to turn less and less blue. And as it turns out, zinc ions don't really have a color, and so this solution would go colorless. If we were to look at the activity series, which shows the strength of different metals, we would see that copper is higher than zinc, which means that copper is a stronger oxidizer, and so it is able to take electrons from zinc. If we were to do this backwards and put a piece of copper metal in a zinc solution, this reaction would not occur. It would be a non-spontaneous reaction. And that's because zinc is not strong enough to take from copper. Copper is only strong enough to take from zinc. Okay, so when you see a problem where it says a solid metal is placed in a solution containing metal ions, it will always be this type of redox reaction. Now, keep in mind, if it gives you an activity series and says, will a reaction occur, that's a different type of question than it's saying, will it happen or won't it happen? But if it just says a copper penny is dropped in a solution of silver fluoride, you're not given an activity series, assume this is a spontaneous redox reaction, which means a reaction will occur. So a solid copper penny, solid copper means that it has no charge, okay, so it's just a straight up solid metal, is placed in a solution containing silver fluoride. And fluoride, that's going to be a spectator ion. So we're just going to have silver, which is Ag+. And when this reaction occurs, we can assume, since it's a spontaneous redox reaction, that electrons are going to be given to the silver in order to form silver solid and copper ions. However, copper forms a 2+ charge, which doesn't match up with this right here, and so we're going to have to make 2 silvers turn into 2 solids. That way we have a place to send 2 electrons to. What this does then is it balances for both charges and atoms, because we have 2+ on this side and 2+ on that side. So when we think about a redox reaction, like the one in the previous problem, it's all about the transfer of electrons. So we know that copper is going to transfer 2 electrons over to silver. Now, normally we just take a chunk of copper, drop it in a silver solution, and this reaction occurs. But look what's happening. We're transferring electrons. So electrons are moving from one thing to the other. Now, movement of electrons, what is that? That's electricity. So what happens then if we capture those 2 electrons and make them go through a route in order to get from copper to silver? So in other words, what if we were to somehow link copper and silver together so the electrons had to travel through perhaps a wire? Then we would generate electricity. And we can use that for all kinds of things, right? Now, as brilliant as I am, I didn't just come up with that right now. It's been around for hundreds of years. We call it a galvanic cell. Now, you know it is something different. We'll get to that later. But it's a device that transfers electrons from one reactant to another through a pathway. So rather than just dropping the 2 reactants together, we put a little pathway between them so the electrons have to flow from one object to the other, and then we can capture that electrical energy. Now, all of these reactions are always spontaneous, which means that delta G is going to be less than 0, a negative number, so that means electrons will flow from one object to the other. Here it is, ladies and gentlemen, the galvanic cell. Now you're noticing it's a little bit more complicated than just a wire stuck between two reactants. A lot of different components that need to be in place in order for this to really occur. And that's why galvanic cells really are in the fairly recent history, even though rust-type reactions or oxidation reactions have been known about for a lot longer than galvanic cells, because they had to kind of figure out all the different pieces. So what we have with a galvanic cell, I'm going to go through the pieces individually here. We have two different half reactions. So this was the very, very first reaction we looked at in this video, the zinc reacting with copper 2 plus to form zinc 2 plus and copper. So on one half we have the zinc half reaction, where zinc solid is turning to zinc 2 plus and releasing 2 electrons. On the other side, we have the copper 2 plus accepting 2 electrons and turning into copper. So the half reaction that involves the oxidation, so the loss of electrons, we call the anode. And then the half reaction that involves the reduction, so copper accepting 2 electrons, we call that the cathode. So then what happens is zinc is losing its 2 electrons and turning into zinc 2 plus. So this metal bar is going to start dissolving, turning into zinc 2 plus. Those 2 electrons, rather than just dropping right off into the solution, are transferred through a wire, and we can use that wire then to power something, a light bulb, an iPod, whatever you need. And those 2 electrons are going to come over to copper. And over here on this copper side, we do have a copper bar, and then we have copper 2 plus solution. So those 2 electrons are going to come over. This copper 2 plus is going to capture those 2 electrons and turn into copper solid. And here's where it gets tricky. So this zinc solid, as it is generating those zinc 2 pluses, those zinc 2 pluses are going to fill into this solution right here. So that means we're going to get an abundance of 2 plus. Now, if we've got 2 plus, and then we've got electrons that are trying to flow away, if this solution is getting really, really positive, those electrons are going to have a hard time flowing because they're going to be attracted to the positive of that solution. So left unchecked, that 2 plus would generate enough force to where those electrons could no longer flow. And so this would stop happening pretty quickly. Enter the salt bridge. So the salt bridge, we put an inert ionic solid in there, something that's going to dissolve and generate ions, cations, and anions. So then what happens, as this solution over here becomes more and more positive, in this case we're using sodium sulfate, the sulfates will flow over into the solution in order to neutralize those 2 pluses, therefore keeping this solution inert, inactive, so those electrons can keep flowing. Same thing over on this side. As those electrons are coming over, it's going to neutralize these 2 pluses that are in the solution, and we're going to wind up with an inert solution, so not enough force to pull those electrons over. So then that means the sodium 2 pluses can flow over here. Sodium 1 pluses can flow over and help keep this solution balanced so that electrons can keep flowing. So without a salt bridge, this reaction would not go to completion. It would occur a little bit, but then pretty soon it would stop because you would get too much positive on this side and too little positive on that side. So take a mental picture of this diagram. This is a galvanic cell. You will be asked to draw these and label the different parts. So let's go over them again once real quick. The oxidation occurs at the anode. The reduction occurs at the cathode. We have 2 metals, our anode and our cathode, and they're both placed in solutions of their ions. So zinc solid and zinc 2 plus, copper solid and copper 2 plus. We have our salt bridge right here, which is an inert ionic solid to where it can flow over to either side. And that'll keep the charges balanced. And then in between we have some kind of object that's going to be drawing the current. So let's look closer at the anode and the cathode real quick. So at the anode, that's where oxidation is occurring. The zinc is going to lose 2 electrons, which means it's going to turn into zinc 2 plus. So over time, the anode will disintegrate. So it would get smaller and smaller until eventually, in theory, you would have no zinc metal left. Over on the cathode side then, those 2 electrons are transferred over, and we have copper 2 plus that was once in solution, turning into copper solid because those 2 electrons are going to neutralize it and form a solid. And so this bar over here, that chunk of copper, is actually going to get bigger as that copper metal sticks to it. So this one's going to shrink, that one will get bigger. And the salt bridge. Okay, so that was the U-shaped tube that we saw before, and inside of there we put a gel or sometimes just a liquid with cotton balls stuck on either end, and in it we had to put soluble ions. So typically sodium or potassium, any of the group 1 metals that never form solids, and then sulfate and nitrate, both of which also are always soluble. And those are used to make your salt bridge. So the ions used in the salt bridge should not and will not play a role in the redox reaction. So you can't use anything that's going to react with either the cathode or the anode to defeat the whole purpose. Rather, they're just there to keep the different half reactions, the half cells, neutral. If they don't keep the reaction neutral, so if it's not there, or if you use something that's not going to work, the reaction will stop fairly quickly. Which means electrons would stop flowing, we'd stop generating electricity, and the world would fall apart as we know it. So then just to zoom in and look at the salt bridge, it's going to have anions and cations, and the anions are going to move towards the anode because the anode is where it's getting more positive, so we have to put some negatives in there to balance that out. And then over on the cathode side, we have the Cu2+, or whatever the cation is, forming into a solid, and so that's going to mean that the solution is going to become less and less positive, and so we'd have to put some of the more positives over there in order to neutralize the solution again. All of this helps generate that electromotive force to where the electrons can flow from one side to the other. If we have too much positive, those electrons won't be able to escape, and if we don't have enough positive over here, the electrons won't be pulled from one side to the other. So then just in closing, a couple other terms. Galvanic cell is one thing you can call this. You can also call it a voltaic cell. And so a voltaic cell means the same thing. It's a cell that generates volts. And then the real world application where you've seen these before is, of course, batteries. So a battery is generally just a type of voltaic cell or galvanic cell that uses this process. It's not quite set up like this. We don't have solutions necessarily. It's typically a paste, but it has all of these different components. It has an anode and a cathode, your positive and your negative end. It has our different salt bridges. It has the solutions and all the metals, and it can flow electrons from one side to the other. And so this little light bulb would just take place between those two guys right there.